Let's take a look at valence bond theory. Valence bond theory is one of two modern theories of bonding, the other being molecular orbital theory, and it's particularly useful for describing the bonding in organic carbon-based molecules. But I'd like to start with something simple, such as the hydrogen molecule, H2. So I have two hydrogen atoms in my molecule. Each one has an electronic configuration 1s1. And valence bond theory tells us that when these hydrogen atoms come together to form a molecule, the 1s orbitals interact. And they interact in such a way that they form a sigma bonding orbital, which is positioned between the two hydrogen atoms. We can show this on an energy level diagram. So if I have a hydrogen atom, there's my 1s orbital, and it has one electron in it. Similarly, my second hydrogen atom, a 1s orbital with an electron in it. In my hydrogen molecule, I've got a sigma bonding orbital, and my 1s electrons are placed in this bonding orbital. Remember, it's between the nuclei of the two hydrogen atoms, so it's holding them together, and the electrons in this sigma bonding orbital are spin paired. In valence bond theory, the bonds have both ionic and covalent character, and that is shown by drawing resonance forms. So for hydrogen, we've got covalent character to our bond. We've got the possibility of ions, with one hydrogen ion being the cation and one the anion, and vice versa. Now in H2, this covalent resonance form is more heavily weighted than the two ionic forms. And because these two ionic forms contribute equally in character, there's no permanent dipole in the molecule. A misconception is that each of these resonance forms exists independently, or that they shuttle between each of the forms like in an equilibrium type arrangement. That is not the case. It's really important to try and think that we've got one wave function for a hydrogen molecule, and it contains both ionic and covalent character, but more heavily weighted in terms of the covalent resonance form. Let's move on to have a look at methane, CH4. Now we know that this molecule is made up of carbon and hydrogen. Hydrogen, each of my hydrogen atoms got the electronic configuration 1s1, carbon 1s2, 2s2, 2p2. And you might be familiar with seeing it written like so. Got two electrons spin paired by 1s. Two of my 2s and one each in a 2p orbital. And this would suggest that carbon is capable of making two covalent bonds. It's got two unpaired electrons, two electrons available for bonding. And yet we know that carbon makes four covalent bonds. So how does valence bond theory explain what's going on? Well, valence bond theory suggests that carbon hybridizes its 2s and its 2p orbitals to form four sp3 hybrid orbitals. So what does that actually mean? Well, we're essentially mixing our s and p orbitals. We're changing the shape and the energy of our atomic orbitals in a way that's going to increase the opportunities for bonding. If we have a look at this on our energy level diagram, we can see that in carbon, if this is my 2s and my 2p, originally I had my electrons arranged like so. If we mix these s orbital and the 3p orbitals, I end up with four sp3 orbitals. They are all identical. They're all degenerate, so they're of the same energy as each other, and that energy is somewhere between the energy of the 2s and the 2p, total amount of energy remains the same, and carbon places one electron in each of these hybrid orbitals. Hey presto, carbon is now able to make 4 covalent bonds. It has 4 electrons available for bonding. If we have a look at this pictorially, we can see that our s orbitals, which are spherical, interacting with our p orbitals, which have direction, they run along the x, y, the z axis, to form our sp3 orbitals. And each of these sp3 orbitals looks a little like so, but you can't really see the little lobe behind in this picture, but just to be aware that it's there. And these sp3 orbitals also have direction. They are what give the methane, our carbon, its geometry. So sp3 hybridisation is consistent with our classic tetrahedral shape. Now, in methane, each of these sp3 hybrid orbitals, remember these are the orbitals that are belonging to the carbon atom, are going to interact with a 1s orbital from each of the hydrogen atoms, because what we're actually trying to make here is methane, so CH4. I'd have my hydrogen atoms bonded to carbon. And when the sp3 hybrid orbitals interact with the 1s orbital from a hydrogen atom, we form both bonding and anti-bonding orbitals. So what would that look like on our energy level diagram? So this is my sp3 hybrid orbital. We're just showing here making one carbon-hydrogen bond. This is the 1s orbital. So this would be carbon. This would be hydrogen. Note that the 1s orbital is of lower energy than the sp3 orbital in carbon. Each of them has 1 electron to contribute to my carbon-hydrogen bond. And when I combine these 2 atomic orbitals, the hydrogen 1s and the carbon hybrid sp3 orbital, I form 2 orbitals. I've got my bonding orbital and my anti-bonding sigma orbital, and that's often indicated with a little asterisk. And in this case, I've got 2 electrons to put in this bond, one from the 1s, one from the sp3, and they would both go into the sigma bonding orbital. And you'll note that it's lower energy, so we have a more stable form. It is preferential for carbon and hydrogen to be bonded than not bonded in valence bond theory. Looking at it pictorially, here I have got my sp3 hybrid orbital and my s orbital on the hydrogen, and they're interacting, and the electrons in the bonding orbital, in the sigma bonding orbital, are placed between the nuclei of the carbon and the hydrogen. And obviously in methane, that is happening 4 times to make CH4. My third example in this quick overview of valence bond theory is going to be ethene, C2H4. So once again, I've got 2 carbon atoms, 1s2, 2s2, 2p2, and obviously 4 hydrogen atoms. Valence bond theory predicts that in ethene, carbon forms sp2 hybrid orbitals. So the 1s electrons are not used in bonding. So if we take our 2s and our 2p orbitals, so there is my 2s, my 2p, so px, py, and pz, we're hybridizing or mixing up the 2s with the 2px and the 2py. Forget about the 2pz for a minute, but we've got 4 electrons in our secondary energy shell in carbon. And so each of the sp2 hybrid orbitals is going to hold 1 electron, and there's going to be 1 electron in the 2pz. So each of my 3 sp2 hybrid orbitals is going to hold 1 electron centred around the carbon nucleus. And in order to minimise repulsion between these orbitals, ethene's got a trigonal planar geometry. This particular geometry is consistent with sp2 hybridisation. So we need to imagine that this is happening for each of our carbon atoms. So I have got a carbon atom. It's got these 3 sp2 hybrid orbitals. One of them is going to be used to form a bond to the other carbon atom, one to a hydrogen and the other to the hydrogen. And we can see here this trigonal planar geometry in operation. So here we have got a sigma bonding orbital between the sp2 hybrid orbital of one carbon atom and the sp2 hybrid orbital of the second carbon atom. And here we've got, again, sigma bonding orbitals, squeeze that in, sigma bonding orbitals formed between the sp2 hybrid orbitals of carbon and the 1s of the hydrogen. So those are the interactions forming these bonding orbitals. And in each sigma bonding orbitals, I'm going to have a pair of electrons. So that's what we can see in this bottom picture. We have got 1 sigma bonding orbital between the sp2 hybrid orbital and the 1s of hydrogen, and here, and then as we can see here, a sigma bonding orbital between 2 sp2 hybrid orbitals, one from each carbon atom. Now remember that each carbon atom has also got a 2pz atomic orbital that was not part of the hybridisation. It didn't get involved. So these are my 2pz orbitals. So what happens here is that the upper lobes of my 2pz orbital merge or interact or overlap, as do the bottom 2 lobes, to form a pi bond. So when we have a look at the classic sort of Lewis structure for ethene, and we see there that we've got a double bond, valence bond theory is telling us that what we've got is a sigma bond, and that holds a pair of electrons, and that is the result of the interaction, if I can spell, interaction between 2 sp2 hybrid orbitals. And it's also made up of a pi bond. This pi bond also holds a pair of electrons. It's from the interaction or the overlap of the pz orbitals on each carbon atom. And this pair of electrons, this electron density, exists both above and below the plane of the carbon-hydrogen skeleton. Might be a good way to look at it. So if I were to draw this out again, we can see here I have got my sp2 hybrid orbitals interacting with hydrogen or with each other, in each case forming sigma bonding orbitals. And then, let's get rid of that, and then my pi bond exists as an area of electron density above and below the plane of the carbon-hydrogen skeleton. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.